Okay, Assalamualaikum warahmatullahi wabarakatuh. Now we continue our part B. Okay, for the chapter 3. For the chapter 4 for the part B. Okay, so look at the activity 4.6. Okay, a triangular channel has side slope 1 horizontal, 1 vertical, and the back slope 0.001 and bending roughness n 0.015 if rate of flow is 0.2 meter cube per second. So determine the type of slope and give the limit of depth of flow in regions 1, 2 and 3. Okay. So first you must use the Manning equation here. Okay, you have learned this Manning equation in chapter 2. Okay, to find the y naught. Okay, so first you must find the y naught. Okay, using try and error or what else you can do. So use to find the y and y naught. Okay, normal y normal using the Manning here. Okay, using the triangular section. Okay, and then so you use to find the yc. So you use this equation. Okay, to the others equation, the other channel. Okay, in chapter 3. Okay, to find the yc. Okay, so we get the yc here 0.3822. So we know that the y naught is more than yc. So this is the types of slope, my slope m. Okay, because you use the y naught more than yc. Okay, so that for for M1 at the region 1, so y is more than 0.5361 here. Okay, for M2, 0 this one to between this ones. Okay, between the y naught and the yc. Okay, and this is you must explain. Okay. Okay, so now we want to analysis of Gvf profile using the three method. Okay, they have three method to analyze of Gvf profile. Okay, actually they have two basic assumption. Okay, two basic assumption that are involved in the analysis of Gvf. So first, the pressure distribution at any section is hydrostatic. Okay, the hydrostatic. Okay, the resistance to flow at any depth can be assumed using uniform flow equation, such as Manning equation, with the condition that the slope term to be used in equation is the energy slope. So you must use the energy slope here. Okay, so this slope SF here. Okay, and then whereas is the hydraulic radius here of the section at depth of y. Okay, so there's the two assumption that you must assume that the pressure distribution at any section is hydrostatic. Okay, and then the GAVF, the depth of flow at any section is y. So the energy slope is SF is equal to n squared over times by v squared over by r power of 4 over 3 here. So use this to get the energy slope. Okay, actually the differential equation of GVF here. So we use this total energy H. Okay, and also the specific energy. So we have learned the specific energy in the previous slide and the previous topic. Okay, in chapter. So this is the schematic sketch of GVF. Okay, actually this is the schematic. Okay, from the E here, energy, specific energy, the Y is the flow depth, okay, the energy line, and the water surface. So this is the sketches of GVF. Okay, actually, since the water surface varies in the longitudinal x direction, the depth of the flow and the total energy are function of x. Okay, actually, no need to worry about this one. Okay, this is for the explanation, theory and explanation. Okay, you just know that how to so this red line here is the dynamic equation that used in GVF. Okay, actually this dv dy over dx. So this is to find that in analysis of GVF. Okay, so and other form that dynamic we use to GVF is K, using the K conveyance at any depth. Okay, Okay, is the conveyance is any depth. Okay, why? And cannot is conveyance corresponding to the normal depth. Why not? So actually the K is equal to Q over SF here for the GVF. Okay, and K naught is equal to Q over S naught here is for uniform flow. Okay, so this is the equation that we use in the GVF, and also the Z is the section factor at depth Y, and S is the section factor at the critical depth. So we have learned the section factor and conveyance is the previous slide in the previous topic. So this is we have learned more than the other topic. Okay, so we use all the value all the equation that we have learned in chapter 1, chapter 2, and chapter 3. So we use all that equation in this chapter. Okay, all the equation we have learned, so you must use, okay, in this chapter. Okay, so this is substituting the into the GVF dynamic equation, so we use this one. Okay, so the x so this is the all the equation that we use in the GVF dynamic equation. Okay, okay, actually, and also this one. Okay, no need to worry about this one. So we look just the other. Okay, and another form of the GVF dynamic equation is dE over dx is equal to S naught minus by SF here. So this is the equation that we use in analysis of GVF. Okay, so we look at the analysis of GVF. So we have among the importance are determines of the effects of radial structure to the flow, okay, in addition due to dam or weir construction and estimation of flood area. So this is the important if in your question or in your final or in your test 2 ask you to state that the importance of GVF profile, so you can state that determination of effects of hydraulic structure in undulations due to dam or weir and so on, the estimation of flood area. Okay, and for analysis of GVF profile, we have learned the three method. Okay, direct integration, numerical integration, and direct step method. So this is the three method that we have learned in Gvf analysis. Okay, so direct integration, numerical integration, and direct step. So we look at the first calculation of GVF profile, gradually varied flow. So we know that this one. Okay, actually the change in depth of flow, we call it as the y over dx can be calculated if y1 and n plus 1 are known. Okay, or L is known. L is actually the length. Okay, the length of the profile. Okay, and also the y we know, and also we this one. Okay, we know that the y1 first here and also the last one here. Okay, so we can calculate using the that method, three method there. Okay, direct integration. Okay, okay, direct step and so on. Okay, so we look at the direct integration here. Okay, first method we use the direct integration method. Okay, for the direct integration method we use this equation. Okay, the equation of direct integration are this, we use this one. Okay, actually all this equation is given. Okay, no need to worry, all this equation is given in your test 2 or in your final. Okay, all this one. Okay, when you at this one is this one. Okay, and the v here, okay, the v here is using this equation, and the u here is this one. Okay, and the j, and the j here is this one. Okay, so this is direct integration. Okay, m n is hydraulic exponent. Okay, m n is the hydraulic exponent, and f v j is same function as fu, this varied flow function, and same function of fu n here. Okay, so m, so you must know that the m, so this is also given the equation, and also the is also the given for the n. here. Okay, so actually for the M and here, M and the N here, so the rectangular is given as 3 and is between this one and trapezoidal 3 to 5. Okay, and so MN is given. Okay, no need to worry about this one. Okay, you just know that the real equation that to find the M, this is given. So this is given. Okay, and also this also is given. Okay, is given in your test 2 or in your final, so no need to worry about this one. Okay, to get the M, okay, and N here. Okay, to get the value of M then N. Okay, so and also the part of the M also we get from this chart. Okay, so no need to worry because M is always given. Okay, no need to find from this chart. Okay, and also this one. Okay, this is just for your knowledge. Okay, so MN is you can find from this table. Okay, this table is given to you to find. Okay, and also so okay, varied flow function for positive slope and F and U. Okay, this is for the calculation of this one. Okay, so first we look at the direct integration method. Okay, first you must calculate y naught, okay, and yc. Second, determine n and m here. And third, calculate j, calculate u and v, find f function of u and n, and function of v and j, and calculate length of ridge. So this is step by step to using the direct integration method. Okay, so this is step by step. Okay, so look at activity 4.7 here. Okay, a very wide river with meaning roughness and 0.035 has uniform depth and m the longitudinal slope of 0.005 based on direct integration method. So this is mentioned. Okay, the method is mentioned in this question, direct integration method. Okay, estimate the length of non-uniform flow to find the length here. Okay, to find the length. Estimate to find the length of non-uniform flow produced by a weir that caused the water surface from y naught 3 meter to 4.5 meter. So this increase as much of 1.5. Okay, from 3 meter increase 1.5 to 4.5 meter. So we want to find the length. Okay, from y naught to the y 4.5 meter. Okay, so this is the basic step that we must know how to use step by step to find the length of this non-uniform flow, okay, in this weir. Okay, first calculate y naught and yc. Okay, so you know that the y naught is 3 meter. Okay, calculate yc. Okay, to get the calculate the yc because this is the wide channel. So for the very wide channel is the rectangular channel, wide rectangular channel. So we assume that r is equal to y here. Okay, so you must use this equation, okay, to find the q. Okay, the discharge per meter cube per second per meter. Okay, until you get here. So we have the y naught. Okay, put the value of y naught here and the s naught and also the n. So we get the q here. Okay. After we get the q, so you must to find the yc. Okay. Yc using the very wide channel. So you'll get the yc here. Okay. Okay. After you get the q and yc, so we know that the surface profile of this channel is y is 3 meter to 4.5 meter. So the y naught is 3 meter. Okay, yc is 1.175. So this is y naught more than yc. So this is in M1 profile. Okay, so you must know that the profile of GVF. Okay, so step 2, determine M and N. Okay, so determine M and N because this is the rectangular. So we just give you the M is 3 and N is 10 over 3. Okay, so this is given. Okay, to find the m and n, so this is given. Oh wait, actually this is given at the previous slide there. Okay, step 3, calculate j. Okay, so j is using this equation. Okay, using this equation. Okay, the j. So put the value of m and n in this j. So we get the j is 2.5. Okay. To calculate u1, u2, v1 and v2, so we use this equation. Okay. We must have the y1 and y0. Okay. So y1, so actually y1, we don't know that y1. Okay. For this question, so we know that y0 is 3. Okay. So you must do that. We assume that the y1 is plus 0.001 until 0.003. That's why from the y1 knots, we get the y1 is assumed that 3.003. Okay, so we get the u1 is 1.001. Okay, and u2 we had here. Okay, 4.5 divided by 3, so we get the 1.5 here. Okay, so this one. And v1, okay, use this equation, put the value, so we get the value this one of the v1, and also the v2 we get this one. Okay, so after we get this one, step 5, now we find the fu1 and fu2 and this one. Okay, actually for this one and this one, we must look at the, okay, we must look at the fu here. Okay, fu, sorry, fu here, fu to n and fv1j, and also this one. So we look at this one. Okay, so we look at the f 1.001, 3.333, f 1.5, 3.333, this one. Okay, and f 2.5 and f 1.717, 2.5. Okay, so we look at the, okay, so we look at this first. Okay, we look at this first, the highlight. Okay, we look at the first, this one. Okay, so we look at the back to the this one. Okay, look at the un here. Okay, we have 1. Okay, 1.0 is, we look at this one. Okay, and n is 3.3. Okay, so we look at this one. Okay, so we look at the, okay, 3.33. Okay, so we look at the f is from, okay, 1 point. So we look at the 1.01. Okay, to get the f 1.001 and 3.333. Okay, so we know that the u is, we get here. Okay, Okay, we get the pen, okay, the what 0, okay, and 3.33. So 3.33 is here, 3.33 at this part here. Okay, so we just look at the between 3.2, okay, and between the 1.85, okay, at 1.856, okay. Then you use the interpolation to get the value of hex here, okay, to get the value of this part, okay. So you get the value of this one, okay. So at this part, so you get the until you get the value for f2. So until you get the value of this one is this one, okay. So you get the using the interpolation that I show you that value. So you get the value of f1n is 1.607, okay, using the interpolation, okay. Next step, I will give you I show you the how to find that the interpolation, okay. So we look at the f, this one again. So look again at the this one, 1.5, okay. Okay, so 1.5. Okay, so we get the f 1.5 again and 3.33, okay, 3.33 again, okay. So 3.33 is at this part, 3.333, okay, and you look at the 1.5 here, okay, at this part, okay. So the value that near for the 3.3 here, okay, at this x here, okay, is 0.211, and we get 0.211 is 3.2, okay, 3.333, 3.4 is we get 0.177, okay. So we get until after you get the value of x here, so you get the value of this one, 0.1884, okay. So until you get to, so and then for the f, v1 and j also you use the same table, okay, same table that I show here, okay. So you just use the 1.1, okay, 2.5, okay. So use the 1.0, okay. So use also the, okay, to get the f v1 and n, that f 1.001 and 2.5, okay. So you look at the same also here, the 1.001 for this one, okay. So but you must look at the 2.5, so 2.5 is here, okay. So 2.5 is the near value. So you find the value of 2.5 here. Okay, so 2.4 we get 2.931, and 2.5 we call x, and 2.6 we get 2.64. Okay, and this 1.001 and 2.4. Okay, F1 and N. Okay, so until you get from this equation here, until you get the value until you get the value here. Okay, so the process also to find the V2J is also the same table here until you get this one. I will show you how to get this one. Okay, after we get this one. Okay, so after this one, so we get the 0.3342 here. Okay, with the same step. Okay, find that value. Okay, after we get this 4 value here, just put all the value in this equation. Okay, put all these equations, you just put here, and then you get the length of channel here. Okay, using the direct integration method. Okay, after you get the L here, so you sketch the profile here, and we get the N is here. Okay, so this is the part of the direct integration calculation. Okay, so this is numerical. Okay, so after that I will explain again more on direct integration method at the new slide. Okay, how to get the value that we learn in table. Okay, this is just for the general explanations. So after this is the second step, numerical integration. Okay, numerical integration method. So we have the for all sections, so we use this equation. So no need to worry because all this equation is given. Okay, so for the rectangular, so it's given here, and also this one. Okay, dy dx. Okay, so we use this equation. Is more remember here. Okay, just use this for the equation use. Okay, we use the dy over dx. Okay, not dx. Okay, so we use the also dy dx, also dx also we can use. Okay, so we get the dy dx and also dx dy. Okay, so this equation is given. Okay, and this is a very wide channel, meaning so this is the equation that given use. Okay, so this is the same questions in activity 4.7. Okay, but this is using the second method, numerical integration. Okay, estimate the length of non-uniform flow produced by a weir that cause the water surface to increase as much. Okay, this is the same questions, but this is using the numerical integration that the give you the N is for step. Okay, so first calculate y naught also. So this in the same step, you must calculate y naught and yc. Okay, so we know that the same. We get the y naught, we get the q. This is the same calculation as the previous slide, the previous example. So we get the yc, and this is also we get the same. Okay, so just look at the method for this method. So we know that S naught is 0.005, Y naught is 3, YC is 1.175, and the X is the Y over S naught. Okay, so we use this equation. Okay, we use this equation. So you must use this one, and dy is dy over n is actually 4.5 is from the y from the 3 why not to increase to 4.5? So that's why 4.5 minus by 3, and you must divide by 4 step. Okay, so we get the difference is 0.735 meter. Okay, so we get, they have the 4 steps, so they have the 1 2 3 4 row here. Okay, so from the 4.5 minus by 0.375, so we get 4.125. Okay, so 1.125, then minus by this one, so we get a 3.750. Okay, and 3.750 minus by this one, so we get 3.375, and 3.375 minus by 0.375 here, so we get the 3 here. Okay, so to get the y average, so you must do the average of this y. Okay, 4.5 plus 4.125 and divide by 2, so we get the average here. Okay, 4.125 plus 3.750 divide by 2, so we get this value, and so on. Okay, until you get the y average. Okay, so y 1 over yc is y average. So we find from this. Okay, from the equation here. Okay, from this equation, you just put to this column. Okay, and this equation you put to this column. Okay, so just put all the value that you get from y average and yc, so we get this value. Okay, calculate the value here, and from y naught and y average you calculate, you get this value. And then dx, okay, dx is dy divided by s naught. So this one, this column, okay, this is, we call the column 1, this is called the column 2, this is called the column 3, and this is column 4, and this is column 5. Okay, so from this equation here, okay, so you must dy dx this equation. Okay, so column 3 divided by column 4 un times by dy over s naught, so you get the value here. Okay, so we get the value here, calculate until you get, and you just plus all the total here, you get 7.824 meter for this method. Okay, then you just sketch the profile of this channel. Okay, so the length, so there's a difference. Okay, there's the difference length. If we use the same questions but we use the difference method, so we get the length is also different. Okay, so just remember that. Okay, so this is the two. So this is and now we look at the third method, direct step method. Okay, so use the direct step method, we also use this one. So don't worry, because all these equation is given in chapter 4. Okay, so direct step method, so this equation we use. Okay, so also the same equation, the same questions, but this is using the direct step method. Okay, and use the 4 step here. Okay, so look at the calculate, also the same, you find the y naught and yc, you get the y, you get the q, and you get the yc. So the same, because the same question but the difference method. Okay, so look at the direct step method. So we have 1 until to 10 column. Okay, so this is more complicated. Okay, the third method is more complicated, but you must know the which columns, every column they have the value. Okay, so s naught, y naught, yc, and so this is the equation for direct step method. Okay, to first column, so you must find the y. Okay, so the y is dy over dy to get the difference of 4.5 minus by 3, we get the 0.375. Okay, so we just put 1 2 3 4. Okay, they have 5 row. Okay, 4.5, and then the difference of this one is 1.125 and 3.75 and 3, 7, 5, and 3. So this is the step for direct step method. Okay, and then you must find the R here. Okay, R for the white channel. So R is equal the Y here. So this is the same value. Okay, for the white rectangular channel, white channel here. Okay, so and then you find the V. Okay, V you can find from V is equal to, okay, sorry, Q A. Okay, so you find the value of V. Okay, you get the Q, we get the Q, Q. Okay, and we know that Q Q over B. Okay, to get the so you must do all the, you must remember all the equation and you have learned in chapter 1, chapter 2, and chapter 3. Okay, after you get the V here, so you use the V squared over 2G. So you just at the fourth column at the fourth column here, so you just calculate the V squared over 2G, so you get this value. Okay, and then you get the E. Okay, actually E is the energy losses that you use that E. So E is you find from the, sorry, okay, the E is you find from this, the first step that you must know the E here. Okay, E is from, okay, sorry, okay, this one. Okay, E. Okay, E is from this specific energy here, so you use this E. Okay, to get the E in the direct step method, the last method that you use. Okay, E from that, the previous slide, you get the E.